video, we're going to talk about what are called compound inequalities. So I have just a quick definition up here. Compound inequalities are two, possibly more, inequalities joined by two words, either an and or an or. In mathematics, an and is called a conjunction. It means both statements have to be true. An or is called a disjunction, meaning either statement can be true. So if I said, well, we have a midterm exam and a final exam in this class, you understand that to mean both statements or both things are going to be true. You're going to get a midterm and you are getting a final exam. Whereas if I said, well, we're going to have a midterm or we're going to have a final exam, in your mind you think, okay, it's either going to be the midterm or the final exam, right? Not necessarily both of them, one or the other, most likely. And that's kind of the idea behind the or, right? So when we take two inequalities and join them by one of these two words, you're talking about what's called a compound inequality. So how do you solve a compound inequality? The answer is it's not that much more difficult than a single inequality. It's just like twice the work, I guess. So yeah, it's a lot more. Not really. You're just following the same rules and just interpreting the answer at the end. So what I have here is a solved compound inequality. X is less than -2 or x is greater than or equal to 5. So think of all the numbers that are less than -2. Or those numbers we can be thinking of can also be greater than or equal to 5. If you were to envision what your solutions are, what numbers would qualify here, well, we're just thinking anything to the left of -2. That is, anything strictly less than -2. So an open circle at -2, shade to the left. Or anything greater than or equal to 5 is also acceptable. So greater than or equal to 5 would be a solid dot and everything shaded to the right. So someone might say, well, one of the solutions to this is -7. And you're correct, because -7 is less than -2. Someone else might say, well, I think +7 is a solution. Well, yeah, it is. +7 is greater than or equal to 5. As long as it qualifies as one of these two, it is a solution to the compound inequality. So we get a statement that looks like this. Right? Now compare that to an and statement. Think of numbers that are greater than or equal to 3. But at the same time, those numbers you're thinking of still have to be less than or equal to 10. So it's not like, hey, anything greater than 3 is just fine, greater than or equal to 3. Up to a point, because both statements now have to qualify. So if we interpret this, we would say, okay, let's start with 3. 3 is right here. Anything greater than or equal to 3, I would say, well, yeah, anything greater than or equal to 3, but you better make sure at the same time it's less than or equal to 10. So we have to consider both of these statements together before we really conceptualize an idea of where the solution is going to lie, as opposed to here, I just graph all the numbers less than -2. Those are all good. And anything greater than or equal to 5 because of the or. With the and, we have to think what qualifies with both. So anything greater than or equal to 3, yeah, as long as it is less than or equal to 10. So our solution is kind of sandwiched in between these two numbers. And in fact, when we write our answer to this, a lot of times it's not written this way, with the word and actually written in there. Sometimes the and is implied, and that is when we write a combined inequality. So a combined inequality is taking an and statement, a compound and statement, and turning it into one statement that we're not separating it with the word and. Right? What that looks like is, just visualize 3 is to the left of where my solution is. 10 is to the right. So left bound, right bound, x is somewhere in between those. Now, how we do that? We simply do the inequalities. 3 is less than or equal to x. Now keep in mind, that says exactly the statement. 3 is less than or equal to x, or we could simply say x is greater than or equal to 3. That's what that statement means. And here, just as we see, x is less than or equal to 10. Anytime you see two inequalities with one statement joined, of course it's compound, but that will always interpret to an and. This never interprets to an or. These inequality symbols always have to be going the same direction, and if you go least to greatest, they have to be going less than or equal to the whole way. Now, we could reverse this and just as easily say 10 on the right and 3 on the left as far as how this is sandwiched. It feels a little different, but all you'd have to do is reverse those inequalities, but they still have to be going the same direction when you write it. So if ever you try to write something like this with inequalities reversed, one going less than, the other going greater than, you got a problem. They have to go the same direction, and we usually go least to greatest. It's just easier to go that direction. All right, so always understand that as an and statement. Okay, now, these are the final stages to solving and graphing a compound inequality. Let's see ones that aren't already solved for us. Now, like I said, it's not really that big of a deal. You just have to solve these guys individually, and you'll get statements like this. You'll graph those, and that'll be your solution. So we have to solve and graph. We'll take them individually here. Hopefully you know to add 3 to both sides. And then multiply both sides by 2, not divide by 2. So we get x is greater than 8. Does not reverse the inequality. We didn't multiply by a negative. Over here, we are definitely multiplying by a -3. That definitely reverses the inequality. So we get x is less than or equal to -4. This is an or statement. Anything that qualifies here or here is good. We don't have to worry about them together. So as far as my solution is concerned, I graph all numbers that are greater than 8. Everything greater than 8 is good, as is everything less than or equal to -4. That's also good. So close that, shade to the left, and there's your graphed solution to this compound inequality. Okay, number 2, we see we have an and. We just have to keep in mind both statements as we go to graph this. So solving the first one, you're subtracting 5. Shouldn't be too big. And dividing by 2. Again, no reversal of the inequality. We divided by a positive. Over here, I'm going to subtract 1 to get 8. Divide by a -1 or multiply by a -1. Any way you slice it, that inequality must reverse. It now becomes greater than -8. We got to remember, all important and. So all numbers less than or equal to 6, well, careful, yeah. Make sure they're also greater than -8 at the same time. That and, you got that little extra responsibility. All right, so all numbers less than or equal to 6. Well, yeah, but you better be careful. Those numbers still have to be greater than, I'm not doing this the good way, but they still have to be greater than -8. So we get that shaded in between. Now, how we could write this as one final statement, if we go least to greatest, I would write this as -8 is less than x, which does mean x is greater than -8. That's the same statement. And at the same time, x is less than or equal to 6. That's how that statement is written without using the word and. It is implied. All right, well, this last one, number 3, this is definitely an and statement. As I said, whenever it's combined like this, that's always going to be an and statement. Now, there's no sense splitting this up into the 2 individual and statements because we can keep it all together. Take a look at this. I'm covering up this side for a reason. If I said just solve that inequality, well, you'd subtract 1. Well, if I go to the other inequality it's representing, 1 minus 3x is less than or equal to 19, you would subtract 1 the same way. So what we're going to do is we're going to keep this all together and just subtract 1 from the left side of this inequality, from the middle to cancel out the 1s, and from the right. Just keep it all together and you can solve them simultaneously. So what you get is a -6 is less than -3x, which is less than or equal to 18. Same game. What would you do here? Well, you divide by -3, but you better be careful. You do have to reverse this inequality. You're dividing by a negative. Likewise, dividing by a -3, that same number, and you're going to have to reverse that inequality. So if we do that, divide everything by -3, you just got to make sure we reverse all the inequalities. So this one becomes 2 is now greater than, that has to reverse. The negatives cancel. Again, reverse And we get 2 is greater than x, which is greater than negative 6, or literally our solution x is between 2 and negative 6. Now me personally, I would flip this thing around and I would put least to greatest just to go this way. But there's no law saying it has to be done that way. It's just this interprets a little bit easier, a little bit more flow with the number line, because we do go least to greatest on a number line, going least to greatest here. So as far as graphing this is concerned, here's 0, negative 6 is somewhere over here, 2 is somewhere over here. We got to make sure the numbers are definitely greater than negative 6, but at the same time less than or equal to 2. And that would be our graph. Okay, that should at least get us started on these inequalities.